Welcome to today's paper reading. Today's paper is titled WPS-SAM, Towards Weakly-Supervised Part Segmentation with Foundation Models. This paper was published on AR14 by Xinjian Wu and colleagues from the State Key Laboratory of Multimodal Artificial Intelligence Systems and the School of Artificial Intelligence, University of Chinese Academy of Sciences. The abstract introduces a novel approach to part-level segmentation in computer vision, called Weakly-Supervised Part Segmentation, WPS. The proposed WPS-SAM framework leverages the Segment Anything model, SAM, a large-scale pre-trained vision foundation model, to perform pixel-level segmentation of object parts. Unlike traditional methods, WPS-SAM is trained using only weakly supervised labels such as bounding boxes or points. This approach demonstrates significant performance improvements, achieving 68.93% mean intersection over union, MIU, and 79.53% mean accuracy, MCC, on the PartImageNet dataset, outperforming state-of-the-art fully supervised methods by approximately 4% in terms of MIU. The human visual system naturally recognizes objects and breaks them down into meaningful parts. This ability is crucial for interacting with our environment. For example, typing on a keyboard requires precise identification of key boundaries and their functions. However, part-level segmentation in computer vision presents unique challenges. Parts often have complex structures and varied appearances, and there is a lack of annotated data. To address these issues, the authors propose weakly supervised part segmentation, WPS, which uses cost-effective annotations like points or bounding boxes to achieve pixel-level part segmentation. This approach aims to balance the cost of annotation with the performance of segmentation. Figure 1 illustrates the differences in training data requirements for three segmentation tasks. A. Fully supervised part segmentation, which requires dense, pixel-level annotations. B. The proposed weakly supervised part segmentation, WPS, task, which uses sparse, bounding box-level annotations. And C. Weakly supervised semantic segmentation, WSSS, which focuses on object category-level annotations. The WPS approach significantly reduces the annotation burden compared to fully supervised methods, while achieving better performance in finer-grained part segmentation tasks than WSSS methods. Figure 2 presents a comparative analysis of segmentation results using the pre-trained Segment Anything model, SAM, under various modes and our proposed WPS-SAM method. Each color in the visualizations represents a unique category. Panel A shows the original images, while Panel B displays the ground truths of part segmentation. Panel C illustrates the everything mode of SAM without prompts, which indiscriminately segments all elements without considering the specific characteristics of objects and parts. Panel D demonstrates the segmentation results under points form prompts, which may either miss or over-segment certain parts. In contrast, Panel E presents the segmentation results with bounding boxes prompts, which achieve superior part segmentation results. Finally, Panel F showcases the high-quality segmentation results of the proposed WPS-SAM method, which does not require manual provision of prompts, highlighting its effectiveness in automating part segmentation. In the domain of object part modeling, the inception of pictorial structure in the early 1970s marked the beginning of efforts to explicitly model parts and their spatial relationships. The deformable part model, DPM, became a classic in object detection, emphasizing the richness and interpretability of object part models. As technology advanced, the need for fine-grained part segmentation grew, leading to the emergence of self-supervised and unsupervised methods. However, these methods often underperformed and were class-specific. The introduction of datasets like PartImageNet and PACO highlighted the academic focus on part segmentation, though high annotation costs remained a challenge. In weakly supervised semantic segmentation, WSSS, methods are divided into single-stage and multi-stage approaches. Single-stage methods integrate classification and segmentation but face optimization challenges, while multi-stage methods use CAMs to generate pseudolabels, often enhanced by techniques like adversarial erasing and saliency guidance. Recent trends leverage foundation models to generate high-quality pseudolabels, though they still lag behind fully supervised methods. Our approach focuses on part-level segmentation using bounding boxes and leverages SAM to achieve superior performance without the need for pseudolabels. The foundation model SAM, when provided with high-quality prompts, demonstrates impressive performance in part segmentation tasks, as evidenced by preliminary experiments on the part ImageNet dataset. However, a simple approach combining a detector with SAM, termed DET-SAM, falls short due to the limitations of the part detector. To overcome these challenges, the proposed WPS-SAM framework introduces an end-to-end strategy that includes an image encoder for feature extraction, a student prompter for prompt generation, and a mask decoder for mask prediction, significantly enhancing efficiency and performance. Figure 3 illustrates the schematic diagram of the trivial DET-SAM, which involves a simple combination of a detector and SAM. The approach trains a dedicated detector to detect bounding boxes of parts, which are then used as prompts for SAM input. However, this strategy is not optimal due to the imperfect part detector and its lack of effective cooperation with the segmentation module. This limitation is further analyzed in section 4.3, leading to the proposal of an end-to-end strategy that directly generates prompts using SAM's image encoder feature maps for more efficient and better performance. Figure 4 provides an overview of the proposed WPS-SAM framework, which is designed to perform part segmentation in an end-to-end manner using only cost-effective weak labels during training. The architecture of WPS-SAM is composed of three main modules: the image encoder for feature extraction, the student prompter for prompt generation, and the mask decoder for mask prediction. Notably, the image encoder and mask decoder modules, which come from the pre-trained SAM model, have their parameters frozen to preserve the knowledge already acquired and to minimize computational costs. The student prompter, on the other hand, is a lightweight query-based transformer architecture that is learned based on knowledge distillation technology. This setup allows the WPS-SAM framework to autonomously derive semantic prompts and efficiently perform part segmentation tasks. Table 1 presents the preliminary experimental results of SAM on the part ImageNet validation set using various types of prompts and backbones. The table reflects the performance upper bound of the method. Key results include ViTB backbone with bounding box prompts achieving 91.14% mean intersection over union, MIOU, ViTL backbone with bounding box prompts achieving 91.62% MIOU, and ViTH backbone with bounding box prompts achieving 91.8% MIOU. These results indicate the high performance potential of SAM and part segmentation tasks when provided with high-quality prompts and robust backbones. In this section, we discuss the datasets used for validating our Weakly-Supervised part semantic segmentation approach. We utilize part ImageNet, a large dataset with 24,080 images and 158 classes, and PascalPart, which includes 19,740 images across 16 classes with part-level annotations. For evaluation, we employ standard metrics such as mean intersection over union, MIOU, and mean pixel accuracy, MCC. During implementation, we maintain the image size at 1024 by 1024, train the parameters of the prompter, and use the Atom optimizer with a learning rate of 1 × 10 to the power of -4. Figure 5 presents qualitative results of part segmentation on the part ImageNet dataset generated by WPS-SAM using a ViTB backbone. The masks, distinguished by different colors, correspond to various part categories. These high-quality predictions illustrate the practicality of part segmentation across diverse real-world scenarios, highlighting the efficacy of our proposed method. The figure showcases segmentation outcomes for most typical examples above the dashed line and a few challenging cases below it, where parts are either occluded or lack clear semantic information. Figure 6 presents the visualization results of DET-SAM, utilizing faster RCNN as the detector. This figure includes both box-level and mask-level information, clearly illustrating the significant impact that part detection has on the performance of part segmentation. The visualization effectively demonstrates how the accuracy of the part detector directly influences the overall segmentation performance. Table 2 presents a comprehensive comparison of the WPS-SAM method against classical fully supervised segmentation models and state-of-the-art weakly-supervised semantic segmentation (WSSS) methods on the part ImageNet validation set. The key findings show that WPS-SAM, utilizing ViTB as the backbone, achieves an MIU of 68.93% and an MCC of 79.53%. This performance significantly outpaces fully supervised methods of comparable scale by approximately 4% in MIU and surpasses the current state-of-the-art WSSS methods by around 12% in MIU. These results underscore the effectiveness of WPS-SAM in leveraging weakly supervised data for part segmentation tasks, demonstrating superior performance with reduced computational costs. Table 3 provides a detailed comparison of the WPS-SAM method against classical fully supervised segmentation models and state-of-the-art weakly supervised semantic segmentation (WSSS) methods on the Pascal part validation set. The table highlights that WPS-SAM, utilizing ViTB as the backbone, achieves an MIU of 60.49% and an MCC of 71.25%. This performance demonstrates that WPS-SAM not only outperforms classical models, but also maintains a significant advantage in more complex scenes, such as those found in Pascal part, which typically involve multiple objects. The results underscore the effectiveness of WPS-SAM in leveraging the rich knowledge within SAM, even with weaker annotations. Table 4 presents a performance comparison of various part segmentation frameworks, focusing on the underlying architecture of the part detector, referred to as the backbone. The table highlights the mean average precision, MAP, mean intersection over union, MIU, and mean accuracy, MACC, for different frameworks. Key backbones include ResNet 50 and SAM encoder, with notable MAP values of 35.0, 34.2, 24.2, and 26.3. The MIU values are particularly significant, ranging from 63.7 to 68.9, showcasing the effectiveness of the WPS-SAM framework in part segmentation tasks. Table 5 presents a performance comparison of maskformer using different types of supervision on the part ImageNet validation set. The table shows that maskformer achieves a mean intersection over union, MIU, of 65.24% when trained with ground truth masks, while WPS-SAM, using bounding box supervision, achieves a higher MIU of 68.93%. The use of pseudolabels derived from bounding boxes results in an MIU of 56.83%. These results indicate that WPS-SAM outperforms maskformer when using bounding box supervision, but both methods fall short of the performance achieved with ground truth masks. This comparison highlights the effectiveness of WPS-SAM in leveraging bounding box information for improved segmentation performance. Table 6 presents a performance comparison between WPS-SAM underpoint annotation and bounding box annotation. The results show that WPS-SAM's performance is notably lower with point annotation compared to bounding box annotation. This performance gap is attributed to the inability of point annotation to capture the shape of the parts, whereas bounding boxes can reflect this information to some extent, leading to superior performance. This comparison highlights the importance of annotation method in the effectiveness of segmentation models. Table 7 presents an ablation study on the number of queries used in the model. The study evaluates the model's performance under different query quantities, specifically 25, 50, 75, and 100. The performance metrics measured are mean intersection over union, MIU, and mean accuracy, MACC. The results indicate a slight decrease in performance as the number of queries increases to 50, 75, and 100. This decline in performance is hypothesized to be due to the additional convergence burden placed on the model by the larger parameter count associated with higher query quantities. The table provides detailed MIU and MACC percentages for each query quantity, highlighting the impact of this hyperparameter on the model's segmentation capabilities. In this paper, the authors introduced WPS-SAM, a novel weakly supervised prompt learning method for part segmentation. WPS-SAM achieves significant performance metrics, including 68.93% MIU and 79.53% MACC on the part ImageNet dataset, outperforming other methods that rely on strong supervised annotations. The authors also analyzed the performance under different weak supervision types and the impact of various hyperparameters. However, a limitation of WPS-SAM is its reliance on the computationally heavy SAM model, which restricts its use in resource-constrained environments. The authors suggest exploring lightweight variants of SAM, such as efficient SAM and fast SAM, to address this limitation. Overall, this work contributes valuable insights to the field of part segmentation and aims to inspire further research in weakly supervised methods. Thank you for watching.